flying model airplanes and other unmanned flying vehicles. Was in the Air Force. Unfortunately, I didn't have anything to do with drones back then because we didn't have it when I was in the Air Force. They had C-47s, and people might know that. Some of them around for a while. And Congress 340s, but that's been my past, and right now I'm working on a couple of products that I'm trying to get on the market.
Okay, Ed?
Ed Wilson, been in business since '61. We were primarily in the alarm business and invented some stuff that used by colleges and universities. Have a new patent that's supposed to be issued either tomorrow or next week.
Did you go there for an interview?
Where?
At the Denver Patent Office? You said you went in to the Denver Patent Office?
Oh, yeah. That was, you were there. That was some time ago.
Okay.
Just add one thing. I worked on a real fun project once with Lockheed Martin. It was called the Mars Lander. You might have heard about that. Wow. That was a fun project. It was one of the nicest things I did in my life. So,
Bill Myrick, business owner, I have a business here in town. Denver native, have an engineering degree, and I worked at Mark for a few years. And, just kind of a garage, tinker and inventor, and I have a few ideas that I'd like to come down and see what I can learn.
All right. Gary?
Jeremy Nielsen, I'm a patent attorney. I work for a small firm out in the tech center. We also have an office in Boulder. Do anything patent and trademark prosecution related.
So is it right here?
My name is Phil. I'm a business owner for almost, I don't know, like 7 months. I'm in the commercial cleaning business. I was telling a couple gentlemen here, also do construction cleanup. Came here just to learn more about what you guys do. I currently invented 2 products. One's in the process of, we're in agreement with the licensee. See what you guys have to offer.
All right. Pete?
My name is Peter. I'm down in the Springs. I'm new to 3D printing, so I'm just up here to learn.
And Vern?
Yes, I'm Fern Roberts, and I used to belong to the group here. I don't know how many years ago, it's been 2 or 3 or 4. But I have an invention and I have a patent on it. And, so I decided to come to the meeting again and see what's happening. Just to hear everybody else. Did bring some things with me, and I'll just show them.
You're on it? Okay. Later, all right.
What?
Did you want to show the doll now?
Oh, well, I'll wait till later.
Pass it around. Okay, Roberto?
My name is Roberto Schena, I'm from Brenda, and I'm a patent agent. I've been practicing patent law for 13 years or so. So I'm the US correspondent of a few design law firms, so to finding prosecution in the US of US patent applications. I'm an electrical engineer.
Okay, I didn't need character.
I'm Paul Moran. Some years ago I developed a product that rendered wood inconvertible, and we're in the process of retesting and all that stuff now. Getting ready to send it to you for a label, and once we do that, then I'm going to be looking for somebody to help in the market. It's right now to get fire retardant material out of a lumberyard, it costs you about $250 a thousand, and very toxic and so forth. This product is non-toxic, non-caustic, environmentally friendly, and about 1/5 the price. And I'm here to learn as much as I can tail end, my right hand.
Yeah. I might also add, I've got,
There's another question.
oh, sure.
Like the Andrews Barbie.
Yes. Oh, yeah, Vern's assistant.
She's my assistant. And she drives for me, because I have to drive me. I couldn't live without her.
Is anyone in here familiar with the Amcon show that runs every April? You have it. I was collecting, I got some brochures, I can pass these around, you can take them. This is on our calendar, it's April 19th, 20. It's at the Colorado Convention Center, it's free to go, but it only runs in the day, like 9 to 3. But you can go and meet manufacturers, metal, wood, fabrics, textiles, laser cutting, forming, all this sort of stuff. Yeah, machining, molding, so you can talk to these people, and if you've got any of those needs, and get some ideas on timing and costs. So it could be useful to some people. So I'll pass these around. There's just some extras I had, but it's on our website. I'm under everything. So anyway, 3D printing, as an engineer, we made compressor impellers back in the early 90s. Just out of junk plastic, just to size up stuff. So now there's been an explosion of materials, all kinds of plastics, plus metals. Actually, Bob introduced metals the last time. It was the gas turbine fuel nozzles. Pretty impressive. I might also add, and we had one meeting down Denver Public Library downtown. You can go there and play with the 3D printer and like run a project, like do the CAD and you can make one-off piece, cost you nothing, so you can kind of get used to it. They don't want to let you do production down there, but you can kind of get a hands-on feel for a small 3D printer and the equipment without having to buy all that stuff. It's good. I'll introduce Bob and we'll get started. Thank you.
So I'm Bob Olsen. I've been in Colorado since '86, 10 years in tooling and plastic injection molding. In the last 18 years, I've been in 3D printing, primarily plastics. In the last 3 years, I've been in metal 3D printing, and I know a lot about making parts, prototypes, cast urethanes, printing, injection molding, etc. So happy to answer any questions. The company I work with now is called 3D Material Technologies. And we used to have printers in Colorado. We moved them down to our plant in Florida. So, we now have, did you have trouble hearing me?
I wasn't getting a good enough signal.
Okay. We now have 11 metal printers of different sizes, and we're owned by a company called Art Group Worldwide. We have 3 manufacturing plants in Colorado, one in Florida, some in Ohio and Michigan, and then we have a plant in Hungary as well. And we do plastic injection molding, metal injection molding, magnesium injection molding, stamping, and then a lot of 3D metal printing, which eventually will be the biggest of all those businesses because this stuff has taken off. So I don't have much of a presentation. I did bring some parts. It was really difficult to scavenge up any plastic parts anymore. I used to be with a company called Protogenic. That was a premier prototyping company in the Front Range, and then they got acquired and they're just about shut down now. But they did 3D plastic printing, urethane casting for prototypes and low volume production, that kind of a thing. So I know a lot about that. But I'd be happy to answer your questions. I've got some parts that you can come up and take a peek at if you want. Primarily a couple of cast parts, a couple of multi-jet printed parts, and then some metal printed parts as well. I'll give you an idea what the technology is. Yeah. Yeah, I'm not a very formal guy. So that's actually a little picture of the plant there. Those are some of the metal printers. We use what's called DMLS, direct metal laser sintering printers. 2 technologies. We use EOS machines and concept laser machines. most all metal printers are from Germany. The French had a company, but those products weren't very good. And EO, or 3D Systems, which is an American company, now makes a very nice metal printer. And printers are starting to come in from Japan, China, you know, all that kind of stuff. But the primary manufacturers are EOS Concept, Renishaw, and SLM for metal. In plastics, there are literally thousands of manufacturers now. But we'll crawl through a little bit of that. So I just want to kind of talk a little bit about 3D printing and what it's used for, what are the benefits, what technologies are there, what materials are available, what's the difference between, you know, this and sort of traditional manufacturing, and then any questions you've got. Who's used 3D printing here? Nobody? Okay.
My engineering days.
Yeah, if you're developing product, you got to use it because it's the cheapest, fastest way to get a 3D model in your hands, and then you can decide whether your design is worthwhile. And the other thing, I mean, a lot of companies you work with will print not only the thing they think is right, but a couple things on either side of that. So at the same time, they can decide whether their dimension was 3.0 or 3.1 or 3.2 or 2.9, because it doesn't cost very much more to throw some more parts on the build platform. So you can iterate much, much faster with 3D printing than you can with traditional manufacturing processes. So it's very useful for prototyping, aids in product development, you know, less expensive design, iteration, and when you're in the design game, like a lot of you folks are, nobody gets it right the first time, or the second, or the third, or the fourth. It's amazing. I'm astounded at the persistence designers have to get a product right. And if the product's part of an assembly, I mean, then the complexities are just multiplied by a lot. So it's a lot easier to print these parts and figure things out with cheap plastic, fairly cheap metal, than it is to go right into try to manufacture with tools or molds or dies or things like that.
Just a quick question, can you make the actual mold itself?
Yeah.
Either plastic or
Yeah, you can. You wouldn't want to, except in one circumstance, which I will talk about in a few minutes. Okay. And the reason is for example, with plastic, you could print plastic mold halves and get some quick injection molded plastic parts. We've done that. The plastic molds only last 5 to 10 shots. That's plenty for a lot of companies to get real plastic parts in the material of their choice out of injection molding. So that's a very powerful tool.
What is that mold made of?
It's typically, they use a Connex material, like 5160, which is a composite. Yeah, it's a multi-jet printed material. Or you can use an SLA.
So it's not metal?
No, you print these.
You said you can print metal.
You can. And we do. We print for a lot of mold companies, but only in special circumstances. The reason being, the laser width, the melt beam pool, is about 6/1000 of an inch. So you're making big metal parts very, very slowly. And the metal powder is a lot more expensive than wrought metal. So if you can machine something, machine it. If that's a better way to go. And with 98% of the molds made, that's a better way to go. But there are exceptions. And I'll cover the one exception where it really makes sense to print a mold rather than machine a mold.
Are you moving in a direction where that is going to improve, where it can go faster?
Sure. You know, the technology always...
Yeah.
It was interesting. So when I was in plastic printing, the big technologies were SLA. It was the first technology out there. Still a great technology. FDM, and then years later, multi-jet. And then all of a sudden, when the patents came off, you know, the shit started flying. I mean, there was printer companies coming from everywhere. But it took 15 years. In metal, it's happening a lot quicker. It's just, the pace of technology is amazing. And I'll try to cover a little bit of that. I don't want to bore you because it's probably not going to affect what you're doing.
Is there a lot of waste with the metal dust then? Is that what kind of makes it expensive?
A lot of waste?
Yeah, like you have to have like a large volume or weight of metal dust compared to the part size.
No. No. So additive manufacturing, what's cool about it, it's a good question. Did I ask you to ask that?
Well, I was just wondering, because you said the metal dust, let's say we're doing stainless.
Yeah.
Like the metal dust is way more expensive than a chunk of stainless.
It is. The powder is. It has to be gas atomized
Right.
to a certain size. We typically use 30 to I should say 20 to 40 micron powder size of the powder. And so they've got to sift, they've got to create powder with gas atomization techniques. Basically, they blast wrought metal into little pieces and then sift them for the size that we want. So it's quite a bit more expensive. But to your other point, additive manufacturing, you only make what you want. Subtractive manufacturing, you take away everything you don't want.
Right, and then it's.
So in a lot of parts, and you'll see some up here, you have to start off with a big block to get an aluminum tube like that, and all that stuff you throw away. You can recycle it. But additive, you just build that little tube.
Do you, when you do the metal printing, do you have to center the product afterwards?
No.
It's welded together essentially.
It's 99, in our density tests, it's basically, aluminum is not quite as dense as the other materials, but it's 99.5+% dense. So typically, way better than cast, and about the same as wrought metal. So in the old days, you did have to center and infiltrate. Not anymore.
So when you did that, you probably had other design issues because you were going to be shrinking down so that your tolerances.
Right. So this, you don't have any of those issues. You have lots of issues in metal printing, but density is not one of them. Yes, sir.
You were mentioning when we were talking earlier that essentially you can combine some smaller parts into one bigger assembly rather than having to go through an assembly process.
Correct.
To create a masterpiece. Can you use different materials in doing that, and layer materials?
In some technologies you can, but they're not widespread yet. So most technologies you can only use one material. There are some hybrid technologies that use basically CNC equipment. And CNC, they may have 50 to 100 tool changers. They just run over and get a ball end mill, and they'll go back and get something to drill some holes, and they'll go back. Rather than go over here and grab a laser head with a powder delivery system, either wire or powder, and right there they can move around on a 5-axis machine, move around your part and add metal. And it could be copper right now, and they can go over here and get an aluminum head and put aluminum on it. So there are some technologies that will do multi-materials. Most companies won't use those technologies because they have no idea what those properties are. They haven't been tested. Metal companies, we primarily print for aerospace companies, and all they care about is proving that your materials are as good as what they get from their traditional manufacturing processes. So they just build tons and tons of test bars, high cycle fatigue samples, low cycle fatigue samples. They test at cryogenic temperatures, they test at very hot temperatures. And once you can prove that your machines can produce these things, then they will start giving you some work for jet rocket engines, airplane engines, things that go up into space. So it's a little interesting field. It's going to take off, but it's not there yet. So you prototype, and in production, printing can be less expensive than traditional manufacturing. Typically it's not, but it sure can be. In injection molding, this is the one area that you can use metal printing that makes a lot of economic sense. You can do conformal cooling cores that result in much faster cycle times and a lot less part stress. So you can get a better quality part faster. And so if you're doing injection molding, you're making 1 million parts a year, it pays for that metal core, the printed core, very quickly. And I could give you one example in a little bit when we get there. And in medicine, It's very big now because you can make unique, customized parts. So they can take an MRI scan of your hip and make a custom hip implant. But more importantly, they can build interesting matrices for bone ingrowth that you can't do any other way. So that they're much better medical implants than what you get with an off-the-shelf solution. Most of that stuff's not done in the United States because the FDA is really tough to get anything through. But it's a very, very big field right now.
So that would be like a pin or a plate to custom fit in a bone?
It would be, this is an acetabular hip cup, for example, 3D metal printed part. And this would be a matrix, a matrix like that the bone can grow into. You just pass that around you want. Or it could be something like that. They do a lot of testing on this stuff, but it can't be manufactured any other way, so it's kind of interesting.
And the material is stainless typically?
Most implantable materials are either cobalt chrome or TI64 ELI, which is extra low interstitial material. And we run both of those. We do implant work for companies.
You used titanium a while back, is that still out of the way?
Yeah, so titanium and cobalt chrome for medical, if that's what you asked. What's that?
I think they're using ceramics too, or something like that.
Oh yeah, I got a ceramic knee. Zirconia or something like that. It's really good too, at least for the last couple of years. So I'm just looking quickly, and I missed one. I whipped this together over the weekend, but I missed one large technology. But the established plastic technologies are stereolithography, apparatus, SLA, FDM, which is fused deposition modeling, SLS is selective laser centering for plastics, and also I should have put multi-jet up there because that's a very big technology now. So multi-jet can print multiple materials at the same time. So not there in metal yet, but we're there in plastics. So this is a typical part that can be printed with multiple materials. So it's got elastomeric materials and hard materials in the same part. So people right now, like Nike, for $300 you can buy a 3D printed shoe, if you're into that sort of thing.
Are you familiar with super tough nylon?
Yes, that's a Zytel or some DuPont flavor of nylon, yeah. They use it for BMX bikes and things like that.
Yeah, I asked you about Delrin, but isn't that acetal actually? Delrin is a brand name.
Delrin's POM. It's polyoxymethyl methylacrylate, polyoxymethylacrylate. And nylon is, polyamide, PA. They're different materials. And Delrin's inherently lubricious, great for plastic gears and things like that. They don't print that yet. I'm not sure why. The nylons are printed in two ways, either with SLS or with FDM. And FDM is an extrusion process. Anybody ever familiar with FDM? That's the most common 3D print technology. You can go and buy a $200 3D printer, and it uses FDM. Basically, you're shoving a fishing line of material through a heated nozzle, and you're just tracing the part till it's all built up. And I've got some FDM examples over here. I've got some selective laser-centered nylon over here, too. And that spreads the powder out, lasers it. You drop the bed down, spread more powder out, laser the next layer onto it. It's about 92% dense. It's got some great properties. Not nearly as good as injection molded nylon. Or you can also FDM nylon strand. But when FDM, the weakness is those two layers. You print this layer and it cools off, and you print that next layer over it. It doesn't adhere as well as it would in some other technologies. So they'll print a layer this way, then a layer this way, and then back, and so you get some good characteristics. But if you're printing like a snap, you've got a part, you need a snap to hook it up to another part, that snap will break off pretty quickly. So all these technologies have strengths and weaknesses. The really cool new technology in 3D printing is Hewlett Packard. So they announced it's what I would call a binder jetting process. So they jet out parts very fast. So I think you asked about metal and the speed for production. Well, Hewlett Packard solved that problem. So right now they're printing, it's probably PA66, nylon 66, or some flavor of nylon. It has to go through a little centering process, but they get great detail and they get parts fast. So this could be a very viable production technology. And a lot of companies like Ford, and things like that, they're interested in that. And when an automotive company's interested, typically everything they do is high volume. Now we print for General Motors, but it's all exotic Corvette stuff, where people pay a lot to have a strut that's been all hollowed out. They do finite element analysis. It's stronger, but it's a lot less weight, that kind of thing. 3D metal printing won't be mass production for many years for things like automobiles. You need millions, go traditional. In terms of materials for plastics, you have some pretty cool SLA resins. And SLA tends to be, good cosmetics, very accurate technology, but the material properties aren't that good. And you can get PLA, ASA, ABS, ABS-PC, polycarbonate, nylon, PEEK, Ultim. You can now have carbon fiber in your plastic prints. You can have glass-filled materials. They're not the same as injection molded glass because you don't get the fiber orientation. It's typically bead glass. But you can get a lot of different materials in printing now, depending on what you want. And then when you think about taking your part from prototype to production, there's sort of a path you can go through. You can do cast urethanes. You can make casting patterns for metal cast parts with this technology. You can make mold halves like we talked about, where you print a core cavity, stick it in a pocket in a mud set or a machined metal mold base, and injection mold X number of parts before they blow up. You can make final parts if the properties are good enough for you. Yes, sir.
That problem you mentioned with layering, with glass-filled material like nylon, would that help out with that layering problem?
No.
It would.
No.
I was just thinking the crystals, glass crystals might.
The problem is when you injection mold glass-filled material, you have short and long fiber, and when it comes through the injection nozzle, it orientates. The canoes all line up and are all in the same direction, so you get great strength one way, not so great the other way. But in this stuff, it's random. So basically, you're mixing up stuff. With the SLS, you're mixing up powder, and then it centers, and everything's every which way. When you do FDM, you have discrete, that's fishing line, you have discrete, circular, hot things you're laying down there, so you get whatever you get that's in there. And it does not, the fibers don't go between the layers and interlock. So it doesn't really buy you much. It'll be stiffer, but the adhesion between the layers is not any better. So if you're going into production of these technologies, it's good to know their strengths and weaknesses and ask your provider, here's what I need, will this deliver that? It'll be really clear on those kind of things.
It flipped to the next screen on you.
Oh, haha. Let's see. So in plastic, Boeing is probably the industry leader in production parts. And basically, mostly what they make are venting air ducts and so on for their airliners. So they can print in nylon. You can print shapes like this, right? You don't have to make 6 different sheet metal parts, bend them, shape them, and then rivet them together to put in an airplane. And every part for an airplane has about 9 pounds of paperwork. They've got to prove that it does what you say it's going to do, et cetera, et cetera. If they can print one part that takes the place of 5 or 6 different parts and just certify that one part, everybody wins. And that's what they're doing. They've got over 30,000 parts in aircraft with no failures. So it's kind of a cool success story. Metal technologies. The established technologies are laser powder bed, which is what we run at my company. Excellent 3 systems realizer, Matsura, Renishaw. EBM is electron beam. That's a very cool technology because you can stack parts. So we print primarily in 10 by 10 by 10 cubes. We've got one machine that's 16 by 16 by 16. But we can only print, we have to weld everything to a metal plate. So we load a metal plate and then we weld the part to it. So if you take a look, these are really kind of two fun parts. So this is a 3D printed assembly. It's got a rotating ring, but this is how you have to print it. These are the support structures required to tie it to the plate. And of course, you got to use metal support structures, and then you got to get the damn things off. So it's kind of, you don't expect printed a wedding ring, because if you lost it, you print another one.
Oh. Okay.
So that's the part, that's the exact same part with the metal supports on it. So that's welded to a plate, then we wire medium the thing off, and then we hand take the supports off the parts.
What's that for?
It's just a show and tell part.
But I want to know what it's for. What's it used for?
Oh, this particular thing is actually just a ring. Not used for anything.
Okay.
There's a lot of parts that we can't show because we're signing non-disclosure companies. But you could use things like this, for example, is a heat exchanger. And we can print very thin walled aluminum, and it can do heat transfers much better than a machine part. You could never machine a part like that. So companies like that, they're very happy to pay to have these kind of things done. Or figure out how to make that and get it in front of it. Can't be done. It may be lost wax. I'm not sure. Think about it. Why does that thing keep going back? Is that me pressing buttons up here? So our parts we have to weld to a plate, so you can only build one layer. The EBM, you can stack layers. So most companies that do titanium hip cups and hearing aid titanium cases and so on, they use EBM technology. I'd like to get one, but we don't have one. Directed energy binder jetting, there's all sorts of different technologies out there. The hybrid CNC stuff we talked about a little bit, where you can just grab a head with different metals. And
Would you say laser is the most common?
by far. Yeah, they sell, they probably, all told, I think they're probably selling 1,000 systems a year in powder bed. And EBM is quite a bit less than that, and the new technologies are way less than that. But if you're developing a product for casting, they have 3D sand printers, so they can print your molds. They can print your sand cast molds. They don't have to make the shapes and pack the sand and, redo the cores. Thanks, Phil. The cool thing about additive manufacturing is you get, in some respects, total design freedom. You're not constrained by conventional manufacturing techniques. So if you're gonna CNC a part, you've got to be able to reach it with the right cutter. You got to make sure the plastic or the metal doesn't deflect or get heated up and do something you don't want it to do. But you do have to obey some design rules for both plastics and metals. But you get great freedom. You can combine assemblies. You can lightweight product, which is one of the big reasons why it's used in aerospace. So you can take a typical airline bracket and then take a lot of metal away, but put in, do finite element analysis, computational fluid dynamics to make sure the part strength and torsion and ability to perform is just as good or better, and take 30% of that weight out of there. And I was telling somebody, in aerospace flight, if you get a pound of material out, it's worth about $10,000. So a lot less energy used to fire it up into space. On a 737, 787, if you get a pound of material out, you save something like $100,000 worth of fuel over the life of that airplane. So if you get a few pounds out, people will spend a lot of money to get that done. So that's, that's why we're in this business. We're hoping to get a piece of that pie. Metal prototype, can be faster. You can make parts that can't be made conventionally. And I just have a one-page slide on the GE LEAP jet engine fuel nozzle. So that little guy up there, that picture, it took about 10 years to develop this, but the new LEAP jet engine is the most successful new commercial jet engine that's ever been introduced. They use like maybe 19 of these fuel nozzles on every engine. They've got 30 or 40,000 orders already. And what they did was they used to have to machine titanium ceramic and then braze it together. 20 parts, about a 30% scrap rate. They got their engineers together and they said, what can we do? They designed a 3D metal printed part. It's 5 times more durable than a brazed assembly, a lot less scrap, 25% weight reduction. It's faster and cheaper to produce. The only problem is they need 45,000 of these a year, and there are not enough printers in the world to do that. Plus, they have stringent requirements to be able to print these things. So they bought 2 metal machine manufacturers, GE, just this year for a couple $1 billion, way more than they're worth, I'm sure. They have put in a $1 billion factory in Alabama, and they are putting in training programs at several junior colleges down there to teach kids how to run these machines. So they are developing a whole infrastructure so that they can start meeting demand for these engines. But very cool use of the technology.
How much time to make one fuel nozzle?
I could not tell you.
But I mean, it's not 5 minutes.
My guess is you put something like that in a platform, my guess is probably 4 or 5 days of building. Then you'd have to cut them off with a wire EDM, so say that's a day. You've got to get all the powder out of that pot, out of the internal. So this thing is full of internal passages, where the fuel goes, where the coolant goes. You got to get all the powder out of there. Then you have to stress relieve and heat treat these things. You have to HIP them, heat treat them. So the whole process, my guess, is several weeks long to get.
Is that a relative size of the thing?
I don't know that, actually. That's a good question. I know a guy that knows that. I will probably find out what the actual size of that thing is. They go in engines that are, I think their turbine blade diameters are probably about 8 feet.
They run them in how many per engine? Like 20 maybe?
There's 19 or 20 of them, yes.
So I don't think they're that super big.
I don't think they're that big either.
So there's
You could hold
20 of
it in your
those.
hand.
Maybe that or smaller.
In the engine.
Yeah. So, but that's the power of the 3D technology. And again, in the medical industry, you can create those unique bone-in growth structures. And primarily 3D metal printing is used in orthopedics. 3D plastic printing, they print medical grade peaks now. And you see a lot where a guy will be missing a lot of his brain or his skull. You can put in skull covers and things like that out of plastic that are compatible, with your body and everything else, and so your skin will grow back over it and all that good stuff. So it's going on quite a bit. This is conformal cooling. I should probably have more on this, but basically conformal cooling. So if you're going into plastic injection molding, you can print a core or a cavity, but primarily we do cores, that have cooling lines that will follow the surface of the part. Now, on this part, which is a circular part, you can see the cooling lines go like this. Okay? So typically what you'd have to do is either you drill a hole through the middle and put what they call a bubbler up there to try to get some water up there to cool it down, or you drill 3 or 4 lines all the way through, plug them off. You'd have to drill a couple lines this way and put plugs in there. And so you'd have squared off lines, because the only way you can make those water lines is by machining. So there's a company, a local company called Magpul. I don't know if you guys are familiar with them. They make gun magazines. They build circular magazine ammunition holders, I don't know what you call it, but the,
Drums.
okay, so, and so one of our companies molds for them, and in order, if you build a block of steel, you start with a block of steel and you say EDM that curve in there. The only way you can get water, again, you drill straight lines. So some of those water lines are 2-3 inches away from where the hot plastic goes in, and some of the water lines are within a half an inch. So you don't get uniform cooling during your molding cycle. What we can do is we can print those parts with water lines that follow the shape of the part exactly. So you get totally uniform cooling. And what they get is their cycle times are 20 seconds faster, and the part quality is much better. They don't get warp and twist when the part comes off. So even though it costs them maybe 3 times more, maybe $14,000 or $15,000 for our core versus $5,000 traditional, less than a year of going into production, they got their money back. Because they're paying $75 an hour for a molding machine. They're getting a lot more parts, less rejects for every hour, so it pays itself off very quickly. So that's a great application for everyday life for 3D metal printing. Any questions on conformal cooling? Cool.
Is the passage, you build it in as you layer it up then?
You can do any number of things. So on the curved cores, we actually just build a water line, one water line that goes by and follows the core there, and you could build them on the side too if you want. And then all we do, we build it, and we just get the powder out of it, and you're good to go. So you got curved, circular, and you could make, as long as you keep your cross-sectional areas the same, you can make any shape you want. You can go from diamond to flat, teardrop shape, as long as we can print it and get the powder out without any problem. You can do whatever you want with conformal cooling. And so, tool shops in this area use this for that. We go out to a company called Moldtech in Minnesota that makes lots of little parts for other people. Standard, nozzles, heaters, things like that, where they need cooling, and we do conformal cooling parts for them. And that actually, we don't need to go into that. That's actually the end of what I want to talk about. Any questions?
On that, like say that vent or that cooling fan that you have up there.
Yep.
What would be the cost for the machine and for you to build if somebody came to you with that as a CAD design?
If you built one of those, I'm gonna say it's gonna be about $2,000. If you built 4 of them the same platform, it would be more like $500 each. Well, no, it'd be more like $750 each.
Okay.
So the price drops down fairly quickly if you can get more parts on a platform. And those are good questions to ask when you're talking to people about manufacturing. Yes, Phil?
Why is it cheaper if you put more parts in there? If you make more?
Well, so setup's part of it. Part of it is the laser bed technology. So you got, say, a 10 by 10 plate, and you got one part here. You still got to put powder over the entire plate. So every pass you come across and lay powder across the entire plate, and then you only laser over here. And it's very slow. Say 30 microns is a typical build layer. That means, oh God, my math's so bad. If it was 50 microns, you'd have about 100 layers per inch. Okay, so say you had a 10-inch tall part. It takes a long time just to spread powder, and all this powder over here is not doing anything. When you have 4 of the same parts or 4 different parts, it's not that, the laser draw time is like 22 inches a second. It's very fast.
So the cycle time.
So basically laser draw time doesn't add that much time to the build. The time is more in the recoating and the dropping of the bed. So when you add more parts, you don't pay, like I said, you spread the setup cost around, you don't add that much laser time, so the price drops fairly quickly.
The machine puts that powder on itself. You don't have to manually put the powder on.
No, they have a dispenser side and a receptacle side. So the dispenser side, every layer, it pushes up the height of the layer, and a recoater blade comes across, drags that powder off the supply, and pushes it across the build plate.
Is the materials, as they're spread in, saying you're using nylon, Is it self-binding, or do you have a binding agent between
No.
layers?
No, it's melted, so it binds to the previous layer. And adhesion's very good on all these technologies, but it's not as good in all layer technologies, with the exception of metal. Metal's actually pretty good in both directions, but in nylon, the adhesion perpendicular to the laser isn't as good as the adhesion would be. I said that wrong. The adhesion perpendicular could be very good. This big layer, but this way, if you're doing a thin part, that's where it'll break. It'll break at the layer.
Is there a definite binding layer, or is there an infusion at the bind?
It's pure nylon, and the heat of the laser fuses it to the previous layer. There's no binder. That's on SLS. On binder jetting printers, there's definitely a binder you got to burn out. It's hot up here. Well, thank you very much. I appreciate it. And good luck with your projects.
Do you have any videos, like you can go to your site, we can play?
I have some videos on here, but it take a little while to find them. I should have brought more.
I know that, I thought before you had one or two, those were pretty cool.
That's a laser centered in metal right there. So you can see it takes quite a while to even just do a 30 micron layer. So that was probably it. And this guy here, Drew Roberts, is sharp, he's available to help out if you're using engineering support.
Must be a bunch of processes. I mean, they can't put all those parts in there.
Yeah, that's all friends in one part of it. I should show you what you do. It's sort of again, but I'll show you what you do.
This is all one part?
Yeah. Just one part. Okay.
And our gimmick was, we would get one of those, honey, air, you know, the squeezable thing.
Yeah.
We fill that, that would be nice. We could set out. Aluminum bear.
This is an injection molding part that I used to do with my old complex. Just to show you, I just brought a couple different samples. That was a little similar we used to do at the press for injection molding. We prototyped all that photogenic with cast urethane.
What's type of material is those?
Printers can't do gold. The printers that do gold have very small bill of envelopes. Do you know why?
I was gonna say.
Gold 10 by 10, you spend $50,000, $60,000. Maybe more, I'm not sure.
This is new.
That is probably, you know, 17. It's a nickel alloy. They call them super alloys.
Is that what all this is?
That's 17.4 stainless.
Stainless steel?
Yeah.
How long would it take to make something?
I would say that's probably a 40-hour bill. And it's